All right, guys, Mr. Antonucci here, and we are in the third video for this one, slope fields and Euler's method, and we're actually going to talk about Euler's method here, and this is another method to approximate solutions of differential equations. So Euler's method is a numerical technique for approximating a particular solution of a differential equation, y prime equals f of x comma y. All that notation means is that the derivative is a function of both x and y that passes through a given point x naught, y naught using steps of equal size. So we'll talk about what all that means. We have a graphical representation here, and we'll get to that in a second. So our differential equation y prime, we can think of as dy dx, and we could write that as f of x comma y. That's kind of what we're talking about here. So the initial condition is the point x naught comma y naught. Okay. And then the step size, we call that h. Okay. So what we do is we start at the first point, which is our initial condition. We calculate the slope there from the derivative, and then we move over and up approximately how much it would be to the next point. So the process here is that y1 is equal to, now what we're talking about here, y1 is not the first point, that's actually the second point. You could think of it as the the point you would get when you take the first step. That's equal to the first y value, or your initial condition, plus h times y prime. Okay, so that's the h times y prime is the derivative up, which is going to give you the slope at the initial point, times the small change or the step size, which is h, excuse me, which is going to be approximately how much y changes, okay, according to what we learned about differentials previously. So basically all I'm doing is to get the next point, I'm taking the previous point plus the approximate change in y. Okay, so we could think of this as y naught plus f of x naught, y naught times h. Okay, and then whatever you get, that is going to be your value for y1. Then y2, you just repeat the process, but you use the new point. So y1 plus h times f of x1, y1. Okay, and then so forth and so on. And you could see here that in the graph, we're constructing an approximate solution curve, and it's pretty close to the exact curve. But notice the further away you get from your initial condition, the less accurate your solution curve is going to be. So what we want to do is use Euler's method to approximate the particular solution of the differential equation y prime equals x minus y passing through the point 0, 1, and we're going to use a step size of 0.01. So in this case, what we're trying to do is just basically generate a table of values that are going to equate to points on the approximate solution curve. So it helps if we have a table of values here. So let me set some things up here. Okay, so our initial step, n represents the step we're on, okay, is 0, 1. That's the initial value there. So the first step, all right, so y1 is going to equal y naught plus f of 0, 1 times h, which is 0.1. Okay, so y naught was 1 plus the derivative evaluated at that point. So 0, 1, x minus y would be 0 minus 1 times 0.1. Okay, so you have 1 plus, so negative 1 times 0.1 is negative 0.1, which is going to be 0.9. So this is our y1 1 value, which is 0.9. Now the x value, that always goes up by 0.1. That's how much our step size is. So each time you iterate the process, your x value is going to increase by however much the step size is. So this is 0.1. And if we continue down here, so forth and so on, you would get 0.2, 0.3, 0.4, 0.5, 0.6, and so forth and so on. The tricky part is figuring out the y2, the y values. So y2 is equal to the previous y value, which was 0.9, plus the derivative evaluated at the previous point. So x minus y would be 0.1 minus 0.9 times the step size, which is 0.1. So 0.9 plus negative 0.8 times 0.1, which would be 0.9 minus 0.08, which is going to give us 0.82. All right. And then if we go to the third y value, you would take the previous y value, 0.82, plus the derivative evaluated at the previous point. So x minus y is going to be 0.2 minus 0.82 times the step size, 0.1. So you'd have 0.82 plus 0.2 minus 0.82 times 0.1. You'll end up, I'm just going to wave my hands over it there and get 0.758. Okay, 0.758. Now, as you go through this iterative process again and again and again, you may end up with longer and longer decimals. You want to use as many decimal places as you can, because since each step is dependent on the previous step, you want to be careful about making errors, rounding errors for that. All right, so I want to do one more example with you. Well, let me back up here. The next thing we could do is then graph these points on the XY plane and get an approximate solution curve. Now, this didn't tell us when to stop or how many points to get. I only did the first 4. You could do hundreds of them if you wanted to, but I think this was just to illustrate how to do the process. All right, so moving on with example 7, suppose y equals y of x is a solution of the differential equation dy dx equals xy plus y squared. Use Euler's method with step size 0.25 to approximate y of 1.75. Start with the initial condition y equals 2 and x is 1. So we're going to start here with our table of values here. So n, x, y. We only have to do 3 steps, because to get from our initial condition of x equals 1 to 1.75 with step size of 0.25, we're going to start at 1 and go up to 1.75. It's going to take 3 steps to get there. So we can actually fill in our x column. So the first x value is 1, and then 1.25, then 1.5, then 1.75. The first y value is the initial condition 2. So the next y value when x is 1.25 is going to be the initial y value, or the previous y value, plus h times the differential equation evaluated at the previous point. So 1 times 2 plus 1 squared. And you're going to end up getting 2.75 when we simplify that. That 2.75 is now the y value for our first point, our first iteration. So that's the y1. To get the next y value, what we're going to do is take that y value that we just got, 2.75, plus h 0.25 times the differential equation evaluated at the previous point. So 1.25 times 2.75, so xy, plus x squared, 1.25 squared. This is going to give us 4. And now that is the y2 value. So then we just follow that process again. We take the previous y value plus h times xy, but the xy of the previous value, so 1.5 times 4, plus the x value squared, so 1.5 squared. And then what we would get is 6.0625. Okay, and that is the y value approximately. So the approximate value of y of 1.75 is 6.0625. All right. Well, that's it for this one, guys. Hope that was helpful to you. Reach out if you have any questions, and take care.